Olá! A IUPAP, International Union for Pure and Applied Physics, está interessada em muitas coisas. Dentre elas, a definição das unidades básicas que nós usamos no dia a dia, a manutenção das constantes fundamentais, mas também está muito interessada nos desafios que a ciência tem atualmente. Na área da física são muitos os desafios. Nós temos desafios desde o entendimento das partículas elementares, da matéria condensada, na física nuclear, na biofísica, na astrofísica. Em todas as áreas, ou sub-áreas da física, nós temos desafios. Para que você saiba quais são esses desafios, a IUPAP organizou um workshop especial, que chama-se Entendendo os Desafios da Física Moderna. Cada área da física está aqui sendo apresentada por um líder, membro da IUPAP, e que você terá então agora a chance de entender, através desta apresentação, os desafios que a área apresenta e como os físicos, de um modo geral, estão superando esses desafios para que a física seja um instrumento de entendimento das ciências naturais e que auxilie o homem não apenas a avançar o seu conhecimento, mas a tornar a ciência um instrumento útil da melhoria de vida de cada um existente nesse planeta e nesse universo. Assista e também faça parte do entendimento dos desafios da física moderna. Boa sorte! So now we have the last talk before the coffee break, and will be given by Peter Mohr from NIST. Peter is a key person on this fundamental constant and units, as you know, so he's a special guest for presentation of the C2 Commission. And we are in a moment of very important considerations about fundamental constant used to define new units and things like this. And this is, of course, of general interest because units and constant affects everybody in physics. And so I thank you for accepting to come and talk, and please go ahead.
Thank you for the invitation. This talk is about fundamental constants and units, as the title suggests. The acronym for Commission C2 is SUNAMCO, and that includes fundamental constants and units in it. So this is very on topic for that commission. I'm going to focus on SI units, International System of Units, and these units have a historical connection to IUPAP because IUPAP suggested that the SI be created in the first place to the International Bureau of Weights and Measures, which was done in 1960. And since then, they have been maintaining the SI and updating it periodically. And what I'm going to talk about is the most recent update that we expect to happen. Hasn't happened yet, but it's going to be a very big change. And so that's the topic. I'm going to jump right to the bottom line, right to the punchline, and here it is. The International System of Units will be different. It will be given by the type, the dark type, and that's the whole story right there. It will be a system of units in which hyperfine frequency has a certain value. That's not changed. Speed of light in vacuum has a certain value. That hasn't changed, but what's new is the ones with a blue circle around. The Planck constant will have a certain value. And in fact, that's the value, as far as we know, that it's going to be. The elementary charge has a certain value. The Boltzmann constant is fixed, Avogadro constant, and a constant having to do with light intensity, which is hard to understand. It has to do with perception by people. In any case, this is the whole thing. It's right here. You can forget about base units because they don't play a role. And so now one of my challenges is to convince you that you can actually make measurements by saying this. So that's the first thing I need to talk about. Here are some background information. There's a website from NIST. There's a website at the International Bureau of Weights and Measures. That's the organization that maintains the SI, creates brochure which describes it, and that brochure is being revised and will reflect the new definitions that I just showed you. There are some papers that are relevant. The paper written together with Bill Phillips and Sandra Knotts, who was a retired high school teacher, and this is aimed at students so they can have a resource to understand the new SI. And then there are some more historically oriented papers. There's a Physics Today article by David Newell, which is very nice. The paper below that, starting with Mills, was one of the papers where some of these things were put forward and discussed, and similarly the bottom paper. So I'm going to go through how you get these units, or I should say these constants, to provide you with measurement standards. And frequency, speed, length, voltage, resistance, charge, mass and power, amount of substance, which is the mole, temperature, illumination, and then go on to say, why should we change? What's the point? And then what is the impact on the fundamental constants? Turns out it's a very big impact. And what's the timeline? When is this going to happen? And what has happened so far? And then finally, a conclusion, which there are a couple of guest speakers, namely Max Planck and Maxwell, will have their statements put up. So here is frequency and time. And again, as I said, this hasn't changed. The hyperfine splitting frequency in cesium-133 is a certain frequency. And if you know that, then you can compare other frequencies to that, and so you get frequencies that way. And of course, Dave Wineland has pioneered making this very accurate standard available, and more accurate as time goes by. Eventually, presumably, they will go to a shorter wavelength in order to provide a more fine-tooth comb, but that's not part of this redefinition. That's something for the future, which will sooner or later take place, we expect. Speed and length haven't changed. The speed of light is a fixed number. In the past, a meter was defined to be the distance that light travels in a certain amount of time, and that provided, given the definition of the second, that provided you with the definition of length. But in fact, the subtle difference here is it just gives the speed of light, and that gives the relation between meters and seconds. It doesn't give, it's not viewed as a definition of the meter, it's a definition of a velocity, and you can compare other velocities to that velocity, the velocity of light. I mean, because of Doppler shift and relativity, which depends on V over C, you can derive other velocities from C. So this hasn't really changed. People really measure length with using a wavelength and interferometer, and so knowing C and knowing frequency, you're able to measure length in a way that's more realistic than saying how far light goes in a certain amount of time, which is not really how people measure short distances. So let me go on. It gets a little more complicated when you come to measuring mass and current, which has changed more radically. Now, people measure voltage with the Josephson effect and measure resistance with the quantum Hall effect. These are the most accurate ways that people have of measuring voltage and resistance, and you can therefore get current because you know the Ohm's law, and that's just, so you have all of electrical measurements can be derived from voltage and resistance. So let me go on and see how this fits in with the definitions so far. Well, more detail. The Josephson effect involves h over 2e times the frequency. In other words, you get a voltage in steps of h over 2e times the frequency you apply to the Josephson junction, and this gives you a voltage measurement. And so to know what you have to know what you've got to know what h over 2e is, because you get a certain number of h over 2e's as your voltage. If you don't know what that is, then you don't know what your voltage is. And so that's one of the things that will change with the new SI. The quantum Hall effect, it's a similar situation. Here there's a formula that I think both of these formulas are widely believed to be true, that it's proportional to h over e squared. In other words, the voltage across a Hall device divided by the current is proportional to h over e squared. It comes in steps of h over e squared, and that is the von Klitzing constant, R sub k. The kj is called the Josephson constant by tradition. And so you know those constants in terms of h and e, both of them in terms of h and e. They're different functions of h and e, but you need to know h and e to know what you've measured. And this is one of the driving forces for changing the SI, and I'll explain that later. So if, and here I've repeated two of the definitions that came before, the Planck constant is a certain value, elementary charge is a certain value, and this is in joule seconds, SI units, Coulomb. And so if you know those quantities, then you know exactly what the Josephson constant is, because it's 2e over h. So if you know what e is, and you know what h is, then you know 2e over h in SI units. And so that's a way of measuring voltage in terms of things that are precisely defined, exactly defined, in fact. Same is true of resistance. You can measure using the von Klitzing constant if h and e are both known exactly as they are now, according to the new definition. I shouldn't say now, in the future is when it will happen. These quantities are exactly known. And so this is an advantage, because in the present SI, people realize that they can measure E and H, they can measure Kj and Rk, voltages and resistances in terms of these quantities more accurately than E and H are known. So you measure a voltage very accurately, but you don't know what you've got. And so people made up units. They called it Kj90. They said, well, let's let Kj be an arbitrary number. And so then you have that many units of voltage with the current, with the frequency involved. And the same for Rk. If you make up a number for Rk, then you have a number that you can use for resistance. And these numbers were chosen to be as close to the values that the SI gives at the time, which was 1990. And so those numbers were used ever since. So if you have a voltmeter and you measure voltages, chances are you're measuring it in volt 90s. Even if you're not aware of that, you're only off by part in 10 to the 8, but still, it's not a real volt. It's not an SI volt. So this will change, because E and H will be known in terms of SI units, so you'll be measuring things in SI units. And so that's a step forward. How about the Planck constant? Well, here's the Planck constant. I already showed that, but this has a different result. If you define only the Planck constant, forget about E for a moment, you can measure mass. And how do you do that? Well, there are two devices. One is an electromagnetic scale called the Watt balance, or now called the Kibble balance. And the other is by creating a silicon sphere with a known mass that you can use to compare other masses. So this is how you get a mass, and I'll show how that relates to H in the following. Here is a Kibble balance, and I'll explain briefly the operation of this. It's a two-step process. It's really a scale to measure mass. You have a mass on a mass pan, and you have a radial magnetic field. And if you put a coil in this field and put a current in it, you can levitate this mass. And so you put a force due to the current levitating this mass, and so you know that current, and so you can write that the force is due to the current times an integral over the coil and the B field. And so you have this quantity which gives you the mass in terms of various quantities, which the current involves a measurement of voltage and resistance. So you have measurements of voltage and resistance which go back to the Josephson effect and the quantum Hall effect, and that gives you mass in terms of those. The problem is B times L is some integral over this magnetic field strength times the coil, which is not something that's easy to measure. And so Brian Kibble came up with the idea that instead of trying to measure the coil size, what you can do is go to a second mode of the experiment where you move the coil in a fixed, the magnetic field's the same, and you move the coil, and that produces an EMF on the coil. And the EMF you produce on the coil depends on the magnetic field times the length of the coil, just as this does. So you can eliminate B times L from these equations, and you get the mass in terms of various integers, quantities, frequencies, acceleration of gravity, which you can measure with a precise gravimeter. You can measure that to parts in 10 to the 9 easily. And so in terms of these simple things, except H, and there's H. So you get mass in terms of H. But in the new SI, you will know H. And so this means you can use this device to measure mass in kilograms and get it in terms of these other quantities, which are relatively well known. Frequencies are much better known, acceleration of gravity and the velocity, oh, that's the velocity, sorry, the velocity, which you can also measure with a interferometer. So this is how you get mass with a Kibble balance. There's another way. Well, here's the point. You have this combination V1, V2 over R. And that combination, here it is, V1, V2 over R is proportional to, you work out the algebra and you get it's just H over 4. So all you need to know is H. And you use the Kibble balance, know H, and then you can know your mass in kilograms. And actually, Bill Phillips was one of the long ago pioneers on the operation of the Watt balance, early models at NIST he worked on. Another way to get mass is to get a silicon sphere. If you know you can compare the mass of a silicon atom to the mass of a carbon atom, for instance. And if you go, you can know the mass of a carbon atom if you, for example, you could fix Avogadro constant, and you know that 12 grams of carbon is Avogadro's constant number times the mass of the times the mass of each atom. So you can get a very, very accurate value for microscopic masses. And in addition, you can form a single sphere of silicon that's almost perfect crystal, measure its size, and what you're able to do is use the fact that you know M, so you can measure, if you know H, you can measure the mass of an electron, the mass of the atom in terms of H over M. You can do that with photon recoil. If you have an atom and you absorb a photon, it will recoil, and that recoil depends on H over M, and it depends on the frequency. Again, the frequencies are well known, so you can get H over M. Well, if you know H exactly, then you know M. And to get the mass of the sphere, you have to just multiply by the number of atoms that you have in the sphere, which you do by measuring the size, knowing the lattice spacing, and that tells you how many atoms you have, and so you know the mass of the sphere. That's another approach that works, and the accuracies are not that different. They're comparable. One of the nice things about the Watt balance is it scales. You can measure grams, you can measure micrograms with that process, And with a silicon sphere, you're stuck with a kilogram, and you have to figure out, you have to scale it down. And scaling, you can lose more information by scaling than you can by doing a measurement at the lower mass in the first place. So there are advantages to the watt balance, and it's a more direct use of H. So that's mass. That's how you get mass. Amount of substance. The Avogadro constant is so many particles per mole. And the new definition would just be that the Avogadro constant is a certain number of atoms per mole. In the current SI, it's as many atoms as there are atoms in 12 grams of carbon-12. Well, that's great, but nobody told you how many there are. And so you have to figure that out separately. It's kind of like a trick question. But in this proposed modification, you know how many atoms there are. You couldn't do this in the past, but only recently you're able now to actually get that number with enough accuracy that it's useful. So this would be the defined value for the Avogadro constant. For temperature, that list of definitions includes the Boltzmann constant as being well defined, as exactly defined, I should say. And so if you fix the Boltzmann constant, you can get temperature, because when you measure temperature, you're measuring kT. If you think about all the ways that you can measure temperature, you realize that what you're really measuring is the energy, measuring kT. And so in some sense, K is just a conversion factor that makes a number that you can put on a scale on your thermometer, rather than having the energy in joules, which would be a little awkward. So in fact, here are a bunch of ways of measuring temperature, the various equations that are involved. This is just using ideal gas law or acoustic gas thermometry, noise thermometry. If you look closely, you'll see that everything is proportional to kT. Here's kT explicitly. Here's K4, T, I think that's a 4, yes. And then here's KT again. Everything's KT, and it's always the energy you're measuring. So if you know K, you know T, because you measure the energy, and you have the energy other ways. Okay, and here is the luminous efficacy of monochromatic radiation. What is this? This is the eye's response to light. It's a way of defining the intensity of light related to candles, how many candle powers you have. And so this is useful for people who want to calibrate radiometry detectors. Why change? Well, the kilogram is unstable. Is this 5 minutes? You just have, what? Okay. The kilogram is unstable. Conventional electrical units are not SI units. The current Kelvin is based on the triple point of water temperature. And that's not that well defined because it depends on the isotope. It depends on details of the water. New SI definitions of the kilogram and Kelvin are scalable. In other words, you can use K no matter what the temperature is. You don't have to refer to the triple point of water. And the same is true of the kilogram. You can use the fact that Planck constant is known to get a wide range of masses. And one of the other things that fundamental constants people like is fundamental constants have smaller uncertainties. Now, I'm going to go quickly through the mass problem, and this is something that's been around for a long time. There's an international prototype of the BIPM, which is the current standard for mass. There are 6 copies that go with it, and every once in a while they compare these, and it's once in a long while, because here's when it was first created, here's 1946, they compared them, and here's 1989 or so, they compared them, and they're not the same. This is the mass of the copies relative to the real kilogram, which is this baseline. And they're different, and they're changing. And so that's a problem. Similarly, if you have to wash the kilogram before you use it as a mass standard. So if you wash it, you lose mass, and you wash it twice, you lose more mass. And if you're a theorist, you wonder if this curve ever converges. but they stop at 2. So what happens? So that's the story of the mass not being a good thing as it is. And so that's one of the reasons to change. Now, what about fundamental constants? Well, you get improved values. First of all, the ones that you defined are, of course, exact, but you get more exact. You get the von Klitzen constant. Electron mass is much more accurate. Goes from 12 to 0.46. Same for the atomic mass unit. Molar gas constant becomes exact. Faraday constant's exact. Stefan Boltzmann's exact. Fine structure constant doesn't change because that doesn't depend on units. Energy conversions are all exact. So if you want to do an energy conversion, in the old days, if you change something to EV and change it back, you lose a lot of accuracy because the EV itself is not well defined. But now, the EV will be as defined as any other constant, and the difference between them will be 0. So you'll be able to convert energy without losing any accuracy. Things that are no longer exact, for example, the international prototype of the kilogram, which is the object in Paris, will no longer be exactly 1 kilogram because it was by definition, and that's no longer going to be the case. Similarly, the triple point of water won't be exactly what it is. Molar mass of carbon won't be exact, but the uncertainties are extremely small, parts per billion. And so these are the things that become not exact, but I think in general the trade-off is not a bad one. Here's the timeline for what's happening. Data that determined the values of these constants that I already showed you was due the 1st of July, that's this most recent July, had to be published. The CODATA task group did a special adjustment to come up with those numbers. The consultative committee on units in August, this most recent August, voted to go ahead with the redefinition. They were happy with not totally happy, but they were happy enough to go forward with the definition. Not everybody was totally pleased. The International Committee on Weights and Measures will meet next week to decide whether they want to go ahead, and that's the group that makes the real decision. And I should point out at this point that C2 is putting forward a resolution from IUPAP to support this going ahead. The fact that CCU, this Consultative Committee on Units, has recommended going ahead, it would be good for IUPAP to weigh in and recommend to the International Committee on Weights and Measures, who makes the ultimate decision, that they support going ahead with a redefinition, that they view this as an advantage. So that's one of the topics that will come up, I think, tomorrow. And then the ratification is expected to take place in the fall of 2018, and the date it will take effect is expected to be the 20th of May, 2019. And that day happens to be World Metrology Day, something we all celebrate. I'm being sarcastic. But in fact, this gives people time to get used to the new numbers. People who make electrical meters and everything will have to put the new numbers in. And so it's useful to have that delay. Maxwell had the idea that we could use atoms as a way, I won't read this in detail. But Maxwell had the idea that we could use atoms and molecules as a way to make standards of length, wavelengths, that these would be similar molecules. Now, our molecule is kind of arbitrary because there's so many of them. Which one would you pick? And atoms, it's true too. So Planck had a more fundamental idea, and that would be to use a constants of nature, which is what we're ending up doing. And he realized that not only could you make standards for time, temperature, length, all of that, but you could even transmit it to people on Mars if you could speak to them, and they would be able to make the same measurements. You don't have to send a kilogram to compare, as we would have to do now. We even go to Paris and compare, and that's how we know whether we have a kilogram or not. So that's the story, and this will take place, we hope, very soon. That's it.
Well, thank you, Peter, for the nice presentation and clarifying everything in this field. We have time for a few questions before going to coffee.
Thank you, Professor Mohr. The new SI unit will be a very big event in a physical society. I have one question about the mass. You point out the two possibilities. One is from Planck constant, another one is from the mass of the single crystal silicon. Concerning the second one, the mass will strongly depend on the number of atoms. And I think in this way, then the diameter or the size of your single crystal will be very critical.
That's right. You have to measure the size of the crystal very precisely, know the lattice spacing, which is also measured very precisely, and you know this unit cell shape, and so all of that tells you how many atoms are in a certain volume. Of course, that's all subject to measurement errors. One of the biggest problems is what happens to the surface of the crystal.
Right.
It doesn't stay pure, and so you have these effects to worry about as well.
Another question is about the realization of the new SI unit. Do you think there's any obstacles or difficulties in metrology or all the aspects?
Not really. I mean, the whole thing was put together with that in mind, that they have to be usable. You could always make up a set of units. You could say the mass of electrons 1. That's great, but that doesn't help you measure things. And so these are all put together in a way that you can measure things. I tried to point that out. There's a way to measure each of these things and use them to find your measurement results.
Okay, thank you.
So we have one question there, and then we have another here, and then Bill. Then, yeah, I think that's it.
I would like to extend the previous question, because when we are talking about silicon as crystal, also it is interesting what was error related with reconstruction of surface, because as usually exist those first layers are different structure from the old bulk, and in this case when you have quite big sphere, it could be also important this effect.
Well, that is an effect, and people make very careful measurements. They have various methods of measuring the surface density. In fact, one of the biggest changes in the results recently has been a new method of doing the surface measurements, and they find a slightly different result. I mean, we're talking about parts in 10 to the 8 for all of these measurements. And so that does contribute. It's like 1 or 2 atom thick layer on the surface, and that matters at the level we're talking about. But people have that, they believe they have that under control.
So, Belita?
I have a question about the units, the everyday units. So if you were or if you are an American citizen, how do you feel about inch and gallon and all these? Because from Brazil, I feel what do you think about gallon and inch?
Oh, that stuff. Well,
Yeah, how do you feel about that?
that's an embarrassment to the U.S. It's all based on the SI system. An inch is exactly 2.54 centimeters. That's it. And that's the definition of the inch. Same for the gallon. It's a certain volume. So everything is based on the SI. Even in the U.S., officially, legally, it is in the U.S. But we don't say anything about it in the public.
But Peter, what's happened if a country adopt and is part of the definition and do not use internally? Is this legal?
Well, that's up to the country. There are 54, 5, 6 countries that agree. This is called the Treaty of the Meter. It's a treaty among all these countries. And
But if I sign the treatment and I don't obey?
Well, you can, once it gets to your country, you can do whatever you want. But we have the U.S. official legal definition is the SI.
You accept as a legal?
We accept it as a legal definition, yes.
Okay, wait, we have a one there.
Okay.
Bill? Okay, well, you have that microphone,
Okay, just
so
a
wait, Bill.
very philosophical question. Within this new system, will we be able to measure the variation of the fundamental constant, like the light velocity, for example? In principle, I mean.
That's a very interesting subject, and Bill will be the first to point out to you that you cannot measure variation of things which depend on units, because you don't know whether the units are changing or the thing is changing. The things that are important are things like the fine structure constant, the electron-proton mass ratio. Those you can measure. The units don't matter. And those are the things that really matter in terms of fundamental physics.
So, Bill.
So I want to make a comment on the first question, which was about two different ways of realizing mass, one with Planck's constant, one with a silicon sphere. What I want to emphasize is that it all has to do with Planck's constant. That is, whether you use a Kibble balance or whether you use a silicon sphere, the basis of defining mass, of redefining mass, is that Planck's constant is defined. So in the one case, Planck's constant is used as a mechanical conversion factor for energy, and in the other case, it's used to convert h over m, that comes from a momentum measurement, into a mass measurement. In both cases, the key thing is that by defining Planck's constant, you now have two possibilities for defining mass, one of which is the Kibble balance, one of which is the silicon sphere. But they're not two different, philosophically different things in terms of the definitions of the fundamental constants. They're just two different ways of realizing the new definition of the kilogram, which is based on having a defined value of Planck's constant.
Let me make an addition to what you said, and you brought up an important point, but you didn't say it explicitly, and that is that all of these definitions allow you to make measurements any way you choose, and that you're not tied to any measurement method. So if you can find a new measurement method that works using these definitions, then you'll get a better result. But at the moment, the methods that people use are the best, or I should say these constants are the best you can get from any methods, which means you can't find a better method for realizing units like mass and such.
Right. For the moment, but somebody clever may come along.
But it's free to change. It's free to get better.
Okay, so I think we can close the talk here. Thank you very much, Peter, for the nice talk.